All right. So hi, I'm Björn, and this is the course on performance of database systems. As you can hear, it will be taught in English or whatever I'm speaking, Icelandic with English with an Icelandic accent. How many of you took my course last fall? So a few, not too many. Okay. So before going into the details, I want to tell you a little bit about myself. So I have a PhD in computer science, focusing on database systems from University of Maryland from 1999, which is about 15 years ago, I guess. I worked in industry for a year and a half before joining Reykjavik University, which was then a very, very young university, about to graduate its first crop of bachelor students. I was dean for 4 years, and now I'm back on the floor, having fun with teaching database systems. So my research interests are in multimedia databases, query processing, optimization, done some work on solid state disks. Some of you that were in my course, I told you a little bit about this. If you want to check out my webpage, it's there. By the way, if you have any questions at any time, feel free to interrupt. So I'm teaching this course with another teacher, Grímur Thomas Thomasson. He will take care of the second 2 parts. So he's a master's in computer science from Reykjavik University, did his work under my supervision. Did work on data model and browser server for a multimedia browser. He's a pretty smart guy. The reason he's teaching with me is because he's been working in industry for 20 years on database tuning, basically. And so since the goal of this course is to teach you how to make your applications faster and prepare you for industry, then it's actually really good to have a guy like this working with us. So he basically claims that he's doing cleanup of things that people did who didn't know how to work with databases or not to use them well, and so he's cleaning up. And then we have a TA, Solmundur. He's a bachelor from Reykjavik University from 2013. He's worked in industry for 30 plus years, I think. Interestingly, I've never seen as many database credits on anybody's transcript, actually. He did 44 credits of database work, including a final project. And he did a master's course that is sort of taking this stuff going even further, and he was actually better than all of the master students. So he's a good guy to have this, and he's teaching this. Both of them are with me now for the second time. So looking forward to that. So this is roughly the architecture that we've seen from database systems so far, right? You learned how to code SQL, create programs accessing the database, and we've done a reasonable job of learning how to design the database, how to create indexes, and so on. But we haven't really looked inside the box. Those of you that took the course with me last year, we did a little bit of this. I mean, we opened up the box and looked at what were the components. But I suspect for many of you, this is pretty much the view that you have, right? You know how to design the database and then use it to get data. So the goal now is to open up this black box and look inside. But first have a few questions for you. And maybe you can start by writing down some of the answers. Why should we tune database? Do you have any stories relating to slow database systems and so on? Maybe think in your mind, what is a large database? And then actually let's do the questions one by one, and then at the end you can do the writing. So why should we tune? Does somebody have experience with slow applications? You hit enter and you wait for some seconds and then something pops up, right? You know this story? Often it's actually the network these days, but sometimes it's actually a database. So my favorite story goes back to when I was working in industry. I was working in a group that was doing servicing database systems, and uh, one day I was on summer vacation. A call comes in from Fjölbrautaskóli Garðabær, one of the high schools here. They had a system had been working for several years and it was always fine, and then all of a sudden it just didn't work. And they would type in some data into forms or try to get some reports and wait for a minute, and then they got a ODBC timeout. And what can you do? So there was a guy that went there who hadn't learned database tuning actually, and he looked around a little bit and he found that yes, indeed, there was a parameter in the page called ODBC timeout. It was set to 1 minute. So he changed that to 10 minutes and problem was solved. It did take 3 or 4 minutes to load the page, but it got there. Okay, and then so that was fine. Next week they called and said, well, there was another page that had an ODBC timeout. This time he was on vacation, I was around. So I went there and started poking around and realized that they were actually running fairly complex queries and it was missing an index. So the query was just taking too long. So I created an index and it went down to 3 seconds. So that's why you learn database tuning, so you can do stuff like this. Then actually I had an argument with the administrator because he had a computer which at that time I think had 384 megabytes of memory, and which was reasonable but not very fast, but he assigned 16 megabytes to the database server and the rest was assigned to the web server that was retrieving data from the database server. So I told him, I think that's a pretty, you should probably balance it a little more better. And I said, well, the web server needs space so that it can present stuff to people. And said, well, okay, where's that data coming from? So he gave me 32, that was top. I actually wanted 256 because that was the point. I mean, where's the data coming from? And he said 32, that's top. So when I left, it had 128. That was a compromise. I just never told him. Anyway, so this is why we bother with tuning, because sometimes we get into cases where our applications are just slow and we want to know how to fix that. So what's a large database? So have you worked with data in industry? What's the largest table that you worked with? So let's see. We have a pen here? Okay, so those of you, this is the largest table, 10,000 rows. Anybody? Okay, less than 10,000 rows. Anybody work with this? Raise your hands. In my class, yeah. Well, you had more than 10,000 rows in my class, I think. Yeah, we had 400,000 rows. All right. So, okay, so we got a few people here, maybe 10 to 100,000. Somebody in this range? You can raise your hands, it's okay. Nobody will kill you. Okay, 100K to 1 million. 400,000, okay. So we have, we got a few people here. 1 million to 10 million. Anybody? Okay. More than 10 million? Okay. So we got 8 hands and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 people. So you've never worked with any database. I mean, you have to have, you have to be in one of these ranges, right? Just over 10,000. Okay, so we got one more. Raising your hands is okay. I don't think you will get any stress-related factors, in your body from raising your hands occasionally. Okay, but basically we haven't gotten here. You will, after this course, you will get into this range. Should be fun. Sometimes it will be painful because the first instance we give you of the database to tune will be very slow, and so especially if you don't have a solid state disk, then this will take a while, but you will see the impact of what the tuning does for you. Now, what I think is a large database, I would say more than 1 billion maybe. That's my definition for large. We won't get there, but you'll get the feeling for what has to happen. Terabytes of data, that's what I would call large. But there, database tuning starts to matter much earlier. The school that I talked about, they had some few 100,000 rows, but they had, we have better hardware now. All right, but again, we will be, I think this is roughly where we are in this course. Okay, so then the question is, what does a database system do for us? And now I want you to pick up the piece of paper, right off the top of your head, a few things that the database management systems does for you. Now, you should all have taken a database course, I hope. You will struggle without that. So just go back and think, what did it do for you? Why? What is the services that the database system does? So I'll give you 3 minutes to write things down. So 1 more minute. And if you're listening to the recording at home, you should be writing down stuff as well. Now I want you to turn to the person beside you, and one of you starts with one thing that the database system does, and you talk a little bit about that, and then the other person comes with another thing. And so, share your notes and see if you find some new things that the database system does for you that you didn't realize. So, you can group together in 2 or 3, maybe. And for example, if you come to the front, you sit here. Góðan daginn. Afköst. Við getum kannski fundið, við erum með svona smá upprifjun ham. Nei, bara kannski sest þarna og spjallar við hann hvað gagnsafs er að gera. All right. So now that you've gotten warm up, I want somebody to tell me one thing that the database system does for us. So you can start over there. Keeps our data organized. So, okay. So we got data organization. So I'm going to write on the table here for the recording. I'll just talk and you'll have to imagine this and then we'll go through this later. Here, you want to tell me one thing? Persistence. Okay. Do you remember we had a term that we used in terms of transactions to relate to persistence? Integrity is one thing, but persistence means that it's basically stored forever or until you change it. And we had the D in the asset. I think we called it durability. So that's another term for the same thing. It stays in the database, even if you turn off the computer or the computer, things crash or somehow. Yeah. Integrity, yes. And so we had actually another term that was also related to transactions that we call consistency, that it sort of keeps the data consistent. Correct? Okay, yes, very good. Over there. Okay, so we got relationship that's somehow related to organization, right? So we have these relationships between data that some things are related to each other and so on. It's very good. And this comes down to, you might call this a data model, right? So that's one of the things that provides us. It's a way to structure the data. Next one over. Yeah, okay. Inconsistency links. So you're kind of in the same thing. But if you couple these things together, then you're also looking at these, avoiding inconsistencies or so on, right? Because if there should be some kind of relationship and you have the mechanisms to enforce that, then you're avoiding some inconsistencies. Very good. Yes. Retrieval. What's another word for that? Query rate. So that's one of the things, and you can even go further and say, gives you a query language, gives you a fairly compact language to get the data. Easy way to do this. So in the back. Okay. So you have data analysis. You might do that somehow with the queries, right? But in a particular way. Okay. So that's one thing that we use databases for. We're here again. I think we got maybe you didn't. I missed you. Okay. Calculations that's kind of similar to analysis, right? You can, you cannot just, you can do more than just retrieve the data. You can actually, in the database, you can do some calculations, aggregations, for example. You remember those? That's one part of analysis. So there you're going into calculations. Yes. Yeah. Yeah. Transactions. Very good. Now do you remember the acronym that we had for transactions? The ACID. So we did a couple of these. But what were the others? So we had consistency, and we had the durability. Isolation, allowing you to pretend that you're the only transaction in the world. And the atomicity, that either all the actions, atomicity, in the transaction happen or none of them. Right? And this is a pretty important part of the database system, allowing you to trust basically your code. And what we'll do, we'll spend a good part of our course talking about how to implement transactions, and another good part of how to implement the query language. Anything else? So another thing, you talked about organization, another thing that relates to this somehow is indexing. And that actually also relates to consistency, because we use indexes to implement primary keys, foreign keys, secondary keys actually. I think you did a pretty good job. So that's, it's a fairly valuable tool. And so if we look under the hood, then you'll see pretty much all of these aspects in sort of system components. I mean, you have your SQL coming in, and then what happens is that it gets parsed and it gets optimized, and then the whole plan is optimized. You have an outline saying you have to read this table and read that table and join them together and then select something, and then you have the individual operators, which we'll talk about how to implement that particular join or how to implement that particular index lookup. You have the transaction manager, which is keeping track of the transactions. And there are basically two components that are important. One is the lock manager or the concurrency control manager that is handling the isolation. And then you have the recovery manager, which is handling the atomicity and durability, which is doing logging. It's keeping a log of what you do. One thing that we haven't talked much about is that the database system also sort of worries about getting things from disk into the memory. How to organize this. This is the buffer management. I'm guessing that some of you are taking operating systems while you're taking this course, and you'll talk about buffer management, probably in detail in that course. We'll talk a little bit about it here. So again, we will talk basically a little bit about this, how this is implemented, and that'll be in the beginning. And then we'll go into the query execution part in fairly good detail, and then talk about the transaction manager. Now, it's basically my definition of a database system. It's a collection of algorithms that work very well when the data is on disk and you need to work with it in memory. And so it's in the first part, we'll do a lot of the algorithms part. Okay, so I'm going to give you a little bit of history, and then we'll go into the course and do some review. And by the way, again, if you have questions, please ask them. My son went to school in the US, and the teacher there said it's better to look stupid than be stupid. Because often we don't ask questions because we fear looking stupid, but then probably everybody else has the same question, and you will be admired for being the first one to have the courage to ask it. So don't worry too much. And I don't bite, really. I might nibble. No, I'm just kidding. I don't really bite. Anyway, so again, for those of you that took my course, this will be a little bit similar. But basically, the relational model that we know and love, and it's so simple that we could teach it to our grandmother, was not the first data model. So there were some models called the network model and the hierarchical model, which are variants of the same thing. Basically, what these models had to organize the data was records, similar to what you would find in a regular programming language. So if you went to data structures, you talked about linked list, right? Stacks and trees and things like this. That's basically what you had. All the organization of the data was explicit. So if you wanted to link things together, then you would create links. Queries were basically large programs to read through these links. So it had some features that were good with data and had the persistence part, but it didn't have the query model, and we didn't have any transactions. And we didn't have what you call data independence, meaning that if you changed the organization of the data, if you decided that it was better to link the data up in one way or the other, then you would have to change your entire program, with we'll find out, or you will have found out with relational model. If you split up a table, for example, you can create a view that merges them or joins them, and then you can kind of hide your changes. Then in 1970, Cod came up with a relational model, which is basically just a mathematical model. It's mathematics, and the only thing that he did is to have the insight that it was actually pretty good, or could potentially be pretty good for organizing data in databases, and that was the insight. And the reason was that because it's an abstraction, you would get away from all these pointers and worrying about your programs not working. You could pretty much do this abstractly. Now, of course, at that time there was no system, so not too long after, there were some research projects that started, one at Berkeley, the other one at IBM, and that started looking into how to implement this stuff. Now, it's actually an interesting history because if we go back to this slide, the hierarchical model was sort of embraced by IBM. They created a system called IMS, which is actually still in operation, so dating back to 1968, and people are still implementing systems based on this. It's really good technology, and it's for things that it works. I mean, if you book flights, for example, fairly high chances that you're going to IMS. Technology from 1968. I think it's actually marvelous. But when Cod, who's an employee of IBM, of the research labs, comes and says, this model that we incidentally have happened to embrace and tell people that that's a database system for the future, doesn't work. It has some serious problems, and we should do something else. So how, if you're a manager in a company and your employee does this, what do you do? I mean, it's a research lab, so you don't fire him, but you kind of, you don't listen to him, and you might discredit him and so on. So he really had some trouble. But so it wasn't really until Berkeley embraced this idea that IBM said, okay, we'll do it too. So it's, interesting political things. It turns out, though, that most of the good work on SQL transactions and optimization came out of Almaden at IBM. And we had roughly when they discovered query optimization, when they could show that you could take pretty much an arbitrary query, any query that you wrote, and the system could find a way to implement it efficiently. That's when you had a database system. Before that, without query optimization, without the system deciding how to run things, you have to hard code it yourself. And at that point, you don't really have data independence and so on. So it took about 10 years to go from an idea to something that was working. Oracle, incidentally, was first sold in 1979. The story goes that as a system, it didn't work, but they had really, really good salesmen who were able to convince customers that it was a good idea anyway. And the IBM people actually officially thank Oracle for being so good at selling things, because otherwise, things might have been a little bit different. So then IBM finally came out with a product in 1982 called DB2. People started looking at sort of more advanced things, looking at object relation systems. Now, hash join is an algorithm that we'll look at here. That was in 86. And in 89, there was an algorithm called Aries recovery, which we'll also study in this course. And so you can see sort of at the bottom, we have technology. At the top, we have project or systems. 92, SQL Server came out. 95, MySQL, and we have other systems coming out, and there's lots and lots of new things. So the current status is actually pretty old. I think Oracle is at 12 and SQL Server is at 2014. And there's been other developments that we'll talk about. Some of them go into the column stores and the disk architectures and things like this. So interestingly, if you look at the methods and techniques that underlie database systems, this is pretty much the most recent one, 89. So how is that? How long is that? 25 years? 26, yeah. So meaning that database systems are actually kind of old technology, right? They haven't changed that much for a long time. They've gotten better, faster, more developed, better query optimization and so on, but it's fairly solid technology. The reason why, well, it actually works. So why change a good thing? So the two key components to me, and the ones we'll spend some time on, are basically you have the query model that, because it's a mathematical model, it came with natural declarative query languages, so calculus and then the algebra, and these are actually used. So we taught these in the first course, and people complain a lot that they will never use this. We'll use the algebra and the internal representation. So when we start talking about query optimization, we actually have to use relational algebra, and then calculus is actually underlying SQL. SQL is developed from calculus. You can draw lines fairly regularly between SQL and calculus queries, and it'll be easy to do. But because the queries that you give are basically, this is what I want. It's not how I want it, it's what I want. Then we need the query optimization. The system has to figure out how to use the indexes, how to get the files and so on to bring it to you. And then the other thing is the transactions that we'll talk about: atomicity, consistency, isolation, durability. You should be at the point after this course, if somebody wakes you in the middle of the night and says transactions, you'll go atomicity, consistency, isolation, durability before you even wake up. It should be very natural to you. And then the implementation of that, locking is one way to implement. We'll talk about another way, which is called optimistic concurrency control, which is getting quite popular. And then logging, writing down things that you're doing so that if the system crashes, then you have a way to get the data correct. All right, so that was the very, very brief relational history. Okay, any questions so far? So go into the teaching plan a little bit. So what you need to know relational algebra, SQL. So somebody asked me if I didn't do too well at relational algebra, will I suck at this? And the answer is no. Might be a little bit harder, but it's relational algebra is not very complex anyway, and so we'll get through this. Disk architecture, this with the platters and the spindles and so on. Have to know this. Buffer management, you probably haven't seen. Was buffer management covered in computer architecture? Doesn't look like it. Okay, so we'll get through that. And then you've talked about trees and hashing, right? Algorithms, pseudonyms, maybe even data structures. Did you talk about B+ trees? You talked about B trees, 2-3 trees, red-black trees, something like this, binary trees, of course. But not B+ trees. Okay, so we'll do that. Okay. And hashing, did you talk about what is called the linear hashing or adaptive hashing, that sort of where the hash table grows as you increase the size? All right, very good. Excellent. That's great. Yeah. Okay. So the question is, what if you took the database course in 2013 where relational algebra was skipped? Just go and read the book. It's, if you send me mail, I can make available a lecture on this. It's not really that hard. I mean, if you did discrete mathematics and you've done some of the algebra there, that's basically it. So, but send me mail and I'll put the lecture online. And actually, that one has, I made that people were doing a lot of examples. So if you spend a couple of hours on that, you should be up to speed. That's the theory of it, at least. But it's really just discrete mathematics. So if you've taken that, you should be fine. I can do that, yes. If somebody sends me mail, because I will forget completely when I come out of the room. So if somebody sends me mail asking me to do that, then I'll do that. And so my mail is björn@are you. And this is the way I work. You tell me something, I'll tell you, send me mail. That happens. Or you can actually use Piazza, that's another way. Okay, so but this is sort of the background that we do. And again, okay, so buffer management, I'll talk about that. The two books we have, the main book for the first part is your old database book from Ramakrishnan and Gerke. Most of you hate that book. I don't like it too much either, but it's still the best one. But actually for this course, it's better. I like it a lot better for this course than I do for the first course. And I haven't seen any other books that actually are good for this course. So that's one of the reasons why we kept it. And then we have a book in the second part for the database tuning by Sasha and Bonnet. And this is really a good database tuning reference, so I strongly recommend to get that. Okay, so the course is basically in 3 parts. So the first part, which is roughly 6 weeks, I will talk about the algorithms. We'll go into what's underneath the hood, and we'll talk about how to implement queries, how to, the operators, how to implement query optimization, how to implement concurrency control and recovery and all this. So that's part 1. Roughly 6 weeks, ends with a midterm exam. Then Grímur will take over, and he'll basically apply the knowledge that we had, in particular of query optimization, but also of the other things. And you will do a project tuning a database where you will get really significant speed ups by using these techniques. And then in the third part, which Grímur will take care of, but I will probably be involved, we'll basically look at new developments. So this is the relational model, single server. There's actually a lot happening now on main memory databases, distributed databases, non-relational databases, and we'll do some reading of papers, things that are happening now, and you'll be presenting for this. So this part is designed to really get you good at what you do in industry, and this part is to make sure that you know what's happening and that you can follow the new trends as they come out, and you'll be able to discuss, the pros and cons of things and figure out whether this is something that you should apply in perhaps in your company and so on. So should we take a break now? We're at 45 minutes. So let's take a 5-minute break and then we'll continue. All right. So as I asked during the break what database systems we're using, and so we're going to be using Microsoft SQL Server for these experiments. For some of this, you will get a virtual machine that you can download, but it's probably a good idea if you have. I mean, if you Windows, just to install it, but for the bigger projects, it might be easier just to use the virtual machine. All right, so that was that. It turns out that Microsoft SQL Server matches kind of the description of the book fairly well, so it's fairly straightforward implementation of the concepts, and it has some tools that are pretty nice for looking at the plans and so on. So it's actually a fairly good system to use in the teaching. So if you have objections to this, then sorry. So this is the description of the course. It's roughly what I told you. The reason why we do this is because everything is using database systems, and you need to be good at this if you want to call yourself a good software expert. And then we'll do the algorithms, because without the knowledge of that, then you're kind of lost in how to make the system work well. And do the database tuning, and then we'll do the recent advancements. So learning outcomes. Let's do the English version. So we divide this into 3 steps. Knowledge is sort of what you should be able to talk about and know. Skills is what you should be able to do, and competence refers to your ability to choose and to make decisions. And so describe the architecture. That's roughly what we're doing now. We're getting into this. Once you've done all the all the algorithms, you will be better at this. Describe the impact that the computer architecture has on the performance database systems. You will be able to do that too, because you'll learn the impact of disks and so on. Discuss the development of database systems and impact on the future architecture. That's the 3rd part. That's gonna get you prepared to be able to do this. Skills, trace the operation of major algorithms. So I want you to be able to just run on paper the recovery algorithm, for example, locking, serializability, scheduling, and so on. And so you can see there's 2 parts. One is the query processing optimization. The other one is used for transaction management and the implementation of ACID properties. And then the database tuning should give you the competence to use metadata and queries to study configuration and content of database, just to look at the database, what's in there, and then what am I looking at? Then measure the performance of databases, of queries and systems, and evaluate whether you need to tune or not. And then we'll talk about make simple changes. I mean, we won't look at things like partitioning the database to multiple disks or computers. We won't look at this in detail. So we'll focus on the simple changes, like rewriting your query, perhaps adding an index, things like this, that actually turn out to make a huge difference. Which, the simple stuff. If you get the simple stuff right, typically that's good enough. So these are the learning outcomes, and so I hope you will be able to look at the end of the course and say, okay, I can do this. So what else did I want to talk to you? Okay, yeah. So the syllabus is here. Probably a little bit confusing, but I split that into modules that have a name, and then they have some readings, and then going by the weeks on Tuesdays and Thursdays, which part of the module will be covering. So, for example, now we have the introductory part, then we'll start on Thursday talking about system basics, chapter 9, 10, 13. I will spend Thursday and Tuesday on that. You can see that most of these concepts are 2 lectures, query optimization I'll try to do in 1 to make some room for concurrency control, which will take some time because we have to cover 2 or 3 methods of this. And then recovery, and then we have a midterm that's basically taking these algorithms and doing this. So I'll get back to the midterm in a moment. Then tuning has one that is called system tuning. So this might change a little bit when Grimur prepares more, but that's basically looking at looking at things like tuning the server and tuning hardware and so on, whereas this is more getting into adding indexes, adding the schema, changing the schema, changing maybe data types and so on. And then the last part is the advanced architectures, and then we'll get back to a review at the end. So I will basically, let's look here. So this time plan, I will probably really not have time to do this properly. So it's probably better not to do this. So you'll just have to keep track of the syllabus here and make sure that you have your readings done in time. So some work, but you can do it. Any questions so far? All right. So again, we'll have these lectures. Okay, so I didn't upload my latest version. So Tuesdays and Thursdays. So Tuesdays, we will be in this room, M110. Thursdays, we will be in M201. And the My School has been updated to reflect that. So it should be correct now. Thursdays has a writing screen, so I'll probably try to do more examples and so on Thursdays to get you to work and so on. For those of you that took my course, you'll know what I talk about. Then we'll go into more details, more examples, and so on. And then on Wednesdays, there will be weekly assignments and designed to be doable, hopefully within the 2 sessions. Now, occasionally you might have to overdo it, but the point is to prepare a little bit beforehand, do it within the 90 minutes, and then submit and go back and do something else. So it's not, these are very small things basically, and they're designed to get into the fingers some of the concepts that we talk about here. Yeah. When we'll hand out these assignments, typically I'll try to do that a few days in advance. So tomorrow's assignment will come out today or tomorrow, but that's not, mostly what you need to do is to make sure that you have SQL Server running, and then the assignment is not that hard. But again, so I'll get to the assignments in a bit, but they're not, they are designed to help you learn. They're not designed to fail you in the class or anything. They're designed to help you learn. It's basically points that you do for learning the topics. And if you want to talk to me, I'm always happy to see you, but I won't have a fixed hour. Just send me mail, and again, I don't bite. So if you have any troubles or any things that's bothering you, then please come and see me. Now, I will be away on February 4th, but what I'll do is basically take a recording from last time and I'll just post that, and that will be the lecture for that Tuesday. So you'll just listen to this. So believe it was a fairly good recording of that topic. And then when the midterm exam is here, I will be away, but Grimur and Solmundur will take care of this, and then they'll be with you, and either one of them. And then they take over, and you will see me back at the end. Now, again, for those of you that have been in my class, you know this. My goal is to help you learn, and this is our goal. I don't necessarily think I'm a good teacher, as a good lecturer. If you've been in classes with Luca, for example, he's a brilliant lecturer. I'm not that. But if you are here to learn, then I can help you. Now, I'll do the translation. The teacher could go a little bit slower into things and explain them better, not just go through them quickly. Yeah, okay. The teacher assumes that students have read the book. This was a negative comment, and I thought it was very positive. But I really do this. And those of you that have been in class, you know this, right? I really expect you to read. And I think that if you don't, you will have trouble. Some of the topics, like recovery, for example, if you haven't read, it is extremely hard to understand on the first go. So read, come to class, go back to the book, do some exercises, and you will get it. Some of these things are really complicated, but so you need a couple of iterations to get through them. So I really expect this. Readings are generally, it's a little bit, in the very beginning, it's a couple of chapters that you need to read. After that, it's typically one chapter per week, roughly, and then so it's not excessive. I'll try to give hints about the reading in the assignments and projects just to remind you that some of these assignments, if you try to do them without reading, you will have trouble. And I think this is a well-known, we have this joke that, working on your project for 5 days can often save you half an hour of reading. It's very frequent, I find, that people have been struggling with a project for several days, and then they go to read the bloody book and, oh shit, the solution is here. I can do this. It's no problem. I recommend to at least look at the assignments before the class, because then you'll know relatively lot about, and if you find that you need to read something. And then, please ask questions. If things are complicated, ask questions. Teaching becomes so much better if you tell me what is hard, and you will learn much more. And so this is really an important part. Yeah. And it's a small class, and so we will have a vow of silence that nobody tells what happens in class days here. And so no, it's okay. But the key. So at some point a while back, I was giving like a final review session in a class, and after the review session, I said, "So good luck with the exam." And then one student says, "Well, that's up to you, right?" But no, it's up to you. You're learning. It happens, if I do my job, then it's all up to you. Of course, as you know, people can screw up, and then it's hard. But if I do my job, then it's all up to you. So that's the spirit. So the assignments, we'll have one every week. Total, they will be valid for a total of 5%. I'll try to put them on the webpage. I said a couple of days. That I do this as early as I can. You prepare a little bit before the class. You finish the in class, and you just submit. Don't wait. Don't spend the entire week, entire day writing this. I'll have the deadline at the end of the day, but don't spend too much time on this. You can work together. Typically, sometimes you have to submit on your own, sometimes in pairs. And the grading, this from my previous class, it's very rough. If you just do a decent job, you will get your 0.5%. You don't have to do it perfectly, playing with the text to make it beautiful. No need. If you just get roughly through this. If you, start and you do a little bit, you might get your half. If you don't do it, you get a 0. But the point is the doing. So the grading will be very quick. You won't get feedback. It'll just, if you do this, you'll get your grade. So that's the point. Free 5%, as long as you do the work. And so now if you, and again, try to focus on the concepts. Don't worry about the format or anything. Try to understand what's going on. Why are you doing this? Why are you seeing this, performance or so on? That's what you need to do. It's really in the doing and understanding, analyzing. It's not in the production of the report. And sometimes the delivery will be just very simple, but the key is thinking. So we'll have 4 projects that are valid for a total of 30%. The first one, measure index performance. Second one, measure join performance. Then we have the big database tuning project. And finally, want to take that database and turn it into a main memory database, which is an interesting concept that's sort of moving the data away from the disks and just into memory. And so it should be pretty cool. These are group projects with max 3 students. And I mean max 3 students. You can do it 2, you can even do it 1, but I don't recommend it. I really recommend to find somebody, a partner. 2 is fine, 3 is fine. 4 is absolutely forbidden, 1 is not recommended. Now, these projects will end with a report, and on this one, I want you to, the reports will focus on the analysis and understanding, but you need to write decent reports. So if they're full of spelling errors, badly formatted, we can't read them, can't understand what's going on, then the grade will be poor. Is that my computer? That was yours. Okay. As people that have taken my course know, then I don't recommend having an open computer in class. But I'm not going to enforce it in this course. I did in the last course. I forbid computers, and actually, I think it was a good thing to do. Anyway, but of course, then you must submit your own work and so on, that stuff. Then you'll have 1 presentation. Again, group. I think we'll probably have 3 students per group for this. So we have a decided number of papers, and then we take that number of students and we divide, and I think it will come out to 3. And for that, basically, you need to read a paper. You might need to do some background reading of other papers in the course. Come up with a 25-minute presentation. I think Grímur will meet you before the presentation to go through how you're going to present, just to help you, give you feedback and so on, so that you're well prepared. You allow 5 minutes for questions, and then we will have some. We grade you, and you will grade each other as well. And we'll also be looking at, we want you to take part in the questions, so be prepared and so on. And we try to pick papers that are not horribly heavy on mathematics and so on, but more on the implementation concepts. So the midterm exam will be again in the end of week 6. Now, if you cannot show up for the midterm exam, or if the final exam grade is higher, then the final exam just counts more. So there's no redo exam of the midterm. If you are sick, then you just go to the final. So you should use this to really push yourself to learn the topics, because you need them. First of all, you need them for part 2, and second of all, otherwise they'll fade. Because there's a few weeks until the final exam, which is is fairly heavy on these parts, and so you need that. So just use this to learn it very well. And of course, you have to pass the exam to pass the course. I'll have all the exams available for practice. And the course, somebody asked, so it's the second time I've run the course, or the first time, and I said, no, it's actually been running since 2001. So I've been doing this for a while. It's the second time that Grímur is involved with this, and so we've changed the emphasis slightly, but it's pretty much designed based on my experience with industry, of what I felt people needed to know and didn't know to do decent software implementations. So it hasn't changed much. Now, the other thing I've been asked, is it running every year? We have been running this every 2 years, and definitely not be run next year, because I will be away on sabbatical. So you're doing the smart thing and showing up now. Now, I used Piazza in my course last semester, and I was very happy. I really liked it. So I'm going to use that for all the announcements and all discussions. So there'll be no announcements on my school, and I will not use Facebook. So if you have a group, then you can do it, but I really recommend using Piazza. This is my strong recommendation. But the metadata of the course, the learning outcomes and so on, the assignments, I'll use that because it's a nice feature of my school, and that really helps. But all the discussions, if there are important announcements, I'll try to make sure that you get mail, but otherwise you check this regularly. I actually recommend turning Facebook off while you're learning. I think you cannot be on Facebook and learning at the same time. And I think actually there's research that shows this. And if you think you can do it, you're cheating yourselves out of the learning experience. So I think, would you go to a movie and learn at the same time? No. It's the same thing. One is social, the other one is professional. And the sooner you separate the two, the better you'll be off. But this is, All right. Any questions about the teaching plan? All right. You have a little bit of a deer in the headlights look. So people have asked me, is this a difficult course? And I answer no, but people tell me that the answer is actually yes. But I think it's the same as with everything. The more you put in, the more you get out. And so people have tried to get through this course easily, and I don't think that works. People have gone through this course with, varying degrees of background and put in the work, and they come out knowing a lot. So it's really up to you. I think, I think it's a fairly good course in that I think there's a good reflection between what we teach and what what the learning outcomes are and what you should be examined on and so on, and what we want you to learn. So I think, it's a good course in that. But again, I think it's mostly up to you. Now, I have some data. So last time I gave it, because of recording, people sort of tended not to show up too much. So there were 10 people out of 27 that showed up every time, and then the rest of them basically were doing distance education. And because I knew who they were exactly, I actually went and checked their grades on average and the grades in the class. I was dean, so I could do this. Probably shouldn't tell you, but anyway. And so, but I did this after the class, so when the whole thing was completely finished. And so the people that showed up, they actually had a better average grade than the whole class by 0.6 or something. In the final exam, they had a better average grade than the whole class by a difference of 1.6. And in the course overall, they had a better grade by average of 2.4. So does that mean that showing up is a good idea? I can't say because, there's a causal relationship that could go any way. But basically, I think if you don't show up, you're condemning yourself to distance education. While, it's doable and people have shown that they can do it, but it's known to be harder. And, just the interaction, just the fact that to show up in class, you have to force yourself to prepare a little bit. That means that you keep on track with your reading and your preparation, and so you're learning constantly. Just that, I think, is really the valuable thing. So I strongly recommend to be here, but it's your call. But again, I think the data shows that it's a good idea. Any questions so far? All right. So then I want to talk about a couple of things. We don't have too much time, but I want to talk a little bit about that. Where am I? Yeah. Here. Control that. Yes. So I want to talk a little bit about file organization and indexing, and a little bit about, well, actually about indexing. No, about disk organization. And so I would call this review, because it's really not going into anything that you haven't learned before. You might not know that you learned this, but I think you have if if you just go back and think about it. So let's do this. So this is basically since the database is managing data on disk and doing the organization and so on that we talked about, then it's good to know how it might do this. And that comes down to file organization. And there are different ways to do this. One of them is called a heap file, which is basically just records get inserted in any order. And that's it. You just insert at the end. If you have to delete, you can delete from the middle, and then you might insert in the middle if you have some space, but there's no really organization. It's just a collection of records in any old order. It's called a heap file. Now, you might have a sorted file. For example, if you think about, employees, it might be sorted based on the employee ID, or it might be sorted based on salary or department ID, or, one way or the other. And that might be a good idea if you're doing a lot of if you're always asking for things in some particular order, right? I mean, you do this with Excel, for example, you put some numbers in your sort, just so that the organization makes sense for what you're doing with the data, right? And it's the same thing with files. Might be order. Can you think of what is the trouble with sorting files? It's inserting, for example. You need to find the place to insert, and you need to move data. Or deleting, same thing. You need to find where to delete, and then you need to rearrange. So the maintenance becomes a little bit heavy. And then there's something called hashed files, which is basically hashing but on disk. So you have a hash table. Each bucket corresponds to a part of the file, and there you can insert records. Inside the bucket, they might not be in any particular order, but what is this good for? Well, if you're gonna ask for things based on equality selection, for example, if you're always asking for the records for one employee, I want employee 25. Okay, do the hashing, go there. I want employee 65. Do the hashing, I go there. See what I mean? You don't need to look through the entire file. You can just do your calculation in memory and then just retrieve, and that's it. So hashing. Now, we want to look at a little bit, what are the advantages and disadvantages, and I think, you got to, for example, the advantage and disadvantage of the sorting is that some of these operations are costly. Now, we'll do a very simple cost model that will just say, okay, B is the number of data pages in the file. So, in terms of 8K pages, similar to what you see on disk in the operating system. R is the number of records per page. If you have 8K pages and you have 100-byte records, then you might fit 80 records. And then D is sort of the time of a disk read. And we'll get to it, what that is. So I will make some, I'll just go on through this. So what we want to look at is this. What would it cost in a file with no organization to scan all the records? What it would cost in a file with no organization to find one particular record based on a criteria? Do a range search based on all the records from one range to another. Insert deletes. Now take a few minutes to try to fill this table. Same thing with sorted file based on your knowledge of how they might be implemented. I mean, you've done the algorithms and data structures. You've done cost analysis and so on. And so just very roughly think about this. So the E records per page, but mostly you need to worry about B and D. D is just the time for disk I/O. We'll do it very roughly. Don't worry about sequential versus random, and then just how many databases are in the file. So have you done a heap file? That'd be the simplest one. So if you want to scan all of the records in a heap file, how much would that cost you? You multiply number of pages in the file times the cost to read each. The R doesn't really matter because that's well, okay. So if you had CPU to worry about, that would matter. But if we just worry about disk IOs, then, and typically in databases we tend to look at the disk IOs because those are really much slower than memory. D is the time to read from disk, yes. And because what you do is you basically take the first page and you read that, and you take the second page and you read that, then you don't need to worry about the R. To search for one particular record in a heap file, let's assume it's a primary key. So you're looking for the employer with ID this. You know there's only one. You need B times D, but on average you can stop when you found it. So assuming you look for things that are there, then you actually on average you could stop after half D. Same thing with rotating disks, right? That if you don't know anything, then on average you'll stop in the middle. Searching for a range is a little bit different, right? Because there you don't really know that you found everything. So for that, you actually need to do the whole thing. How about insert for heap file? It's constant, D, or actually probably 2D, because you need to read them, you need to write them. There's a little trick, but you're right, it's constant. It's basically this guy. Delete, same thing. To read the file, make the change, and write it. So some things are easy, some things are hard. Have you gotten through sorted? To scan a sorted file, what do you need? You just need B times D, because you just scan everything. The sorting doesn't really matter. To search for equality, yeah, something of your order of log n or something to maybe of the size times D, maybe, right? For each level you need to find. So you can do a binary search, and that's where you get the log 2. For those of you that have talked about B+3 indexes, then you know that you can actually improve the logarithmic factor significantly. Range query. How do you, if you have a sorted file, how would you implement the range query? You find the first one, and then you scan until you hit the second one, right? So it's kind of, you can think of it as sorted, then you would go here, and then you just stop, right? And so that means you need to do the search, which is O of log 2 of B times D, and then you need to add, you know, number of records divided by R, because that's how many records you have on page, times D. So this is how many pages you would need to look at. Yeah, this is getting complicated, but yes, yes, okay. So basically, you don't have any kind of index. What you do have is a file that is ordered by something. And so in that case, you basically just use a binary search. So just look in the middle, that's going to cost you a D, and then you compare. If it's smaller, then you go here, and that's going to cost you another D, and so on until you finally find the record. And so on average, that's a log 2, because you're looking at always halving the size. Yeah. And so, again, we'll talk about how to estimate the number of records and so on. But the point is here to understand with sorted, you would find the first one, and then you just scan until you find the last one. Inserts in a sorted file. You need to do a complete reorganization, right? So on average, you would insert somewhere in the middle, and then you do the whole, reading and writing. So you do 2 times reading half of this. So read half the relation, or half the table, and write it again. So B times D. Deleting, same, right? You don't know where you're deleting from. Could be the first record, could be the last record. On average, in the middle. And you need to read and write. So this is the average in the middle, and this is the read and write. So you get the same thing. So you can see that heap organization is very good if you have a lot of insert and delete. If you have few of these, but you mostly have like these queries, then this would be very good. Could you mark it as deleted and leave it there? Yeah, yes. So that is one of the assumptions, was that you would actually compact and so on, but you could do that. You can, because typically deletes don't happen that often, and so it might be a good idea to just leave them. Or you can say, okay, I'll leave them. If I'm reorganizing, I'll remove them. If I'm inserting anyway, I can just remove them. So I can do some savings, yes. Hash file. So the assumptions we're making is that hash buckets, they're not always full, but we have decent hashing, so the hash buckets are 80% full. So there's 20% extra space, empty space. So to scan, we need 1.25 B times D, right? Because there's some extra space that we will have to read from disk. So the file is a little bit larger. To search with hashing, how do you search with hashing for equality? You need to find a single record. That's actually the search key. That's the organization. It's constant. It's beautiful, right? And so hashing is great for equality. And we'll find that when we start to do joins, hashing is very good for joins. Searching based on a range for hashing. Constant times the number of values. Yeah, probably have to go through everything. So if you are searching on, let's say, an identifier between 30 and 40, you could technically say, okay, I'll hash 30, 31, 32, 33. Now, some of them will find a match, some of them won't. But if you're looking at, for example, salary or something that's a real number, then that would break down. So typically, hashing doesn't really help. If you're looking at strings, for example, it won't help because there are infinite number of strings. So then you have to scan everything, and you're back to this. Insert. in hashing? Somebody said constant. Did you hear this? Yeah. So this read and write, right? Typically, I mean, occasionally you'll have an overflow bucket and you'll have to fill it up or something, but same thing here. Deletes very fast. So hashing is excellent for this. It really doesn't help you with searching for ranges. There's no help. So did we get it right? Maybe we didn't. So delete said search plus D. That's a good point, actually. To delete, we need to find the thing, which is B times D divided by 2, and then we need to write. All right. Good thing to have this correct. And sorted said the same thing, search plus B plus D. All right. And the search is this part here. So we forgot about searching to find the records that we want to insert, but we have the point. Now this is very rough, but you can see where this is going, that organization actually matters and depends on what you want to do. If you're inserting, deleting, you have one organization. If you're analyzing and scanning, you have another one. And I will get through, we'll talk about indexing, where you can basically combine these things. So you can have multiple indexes that will allow you to play with these in different ways. And we're kind of running out of time. So I think this was really the most important thing. So one of the things that they talk about in the book that might be good to talk about a little bit is when they're indexing, they talk about 3 alternatives of how to organize your index. And the one is basically, I mean, if you think about indexing, it's kind of like hashing, right? You can think of it that one way. When you have, okay, now let me back up. So if you have an index on hashing, you would basically put in each bucket that this is the bucket for hash values between, that range to 1, let's say. That's one of your buckets. And so that's part of the organization. Now, you might, in that bucket, you might have the data, and this is what we talked about in this file organization, where the data is actually part of this, or you might have just a pointer to the data. And I think in data structures, you might be more used to this. You have records and you have pointers to the records. And on disk, the pointer to the record might just be, it's in this page, in this location on the page. And so you can, in any index, you can store the data in the index. And again, this is what we assumed, that when you have the sorted file, the records are in the file. When you have a hash table, the records are in the table. Or you might just have, the ID of the record somehow, a way to find the record on disk directly, so that you can look at the index and then just go to disk, say, here is my record. And there are 2 ways to do this. One is to say, if you're, for example, if you're looking at, if you have an index on departments for your employee table, there might be many employees in one particular department, right? And so what you might have is that for department 10, you have a list of all the employees that are there. Or you might say, for department 10, I have many records. One of it first says, department 10, I have employee 50. And then the next record says, department 10, employee 25. And then department 10, employee 35, and so on. See what I mean? And this one is more compact because you only store the department ID once, but it's more complicated because you don't know how many employees are in each. So this one is actually simple. And I think in all the index you'll find either one of these. Either the data is in the index, or you have each entry has one pointer. So that's, you'll see these organizations occasionally come out, and then so this is what they're talking about. And you can go through this yourself, just look at the files. That's it. So I want to talk a couple of minutes about disks also. But again, you should know this. I just want to look at what is the focus of this. So again, data is stored on hard disks. It's worked within memory, and this means that when we need to read, work with data, we need to read it in, and sometimes we need to write it out. This is what we were getting to in the cost model here. Now, why don't we store everything in main memory? It's too expensive, and actually, when the server stops, then memory fails. Now we have solid state disks these days, which are kind of an hybrid in between. They are actually they're expensive, but not as expensive as main memory, and they are not volatile. So things stay in solid state. So you find new systems where this is kind of in between. Anyway, so you know this picture, right? How many times have you seen it to date? 5 times? All right, cool. So I've always said if you don't see it at least 5 times in your bachelor's degree, something is wrong. So already 5. So we're doing very well. But the point of this picture is to understand, for this course at least, is to understand the impact on performance. And so what do you need to access this page? What are the costs of accessing a disk page on disk? Do you remember the model? You have the heads that need to go to the right track, right? Remember what we call this? Seek time, very good. And then we need to wait for the correct sector to come under the read heads. So what do you call this? Rotational delay. Yeah. And then we need to read. So we have these. All right. So we have these 3 costs. Now, what are these costs? Do you know? Have you looked at specifications of disks? On the rotational delay, on average, you'll have to wait half a rotation, right? The same thing as with the scanning a heap file or searching equality search on a heap file. You have to wait half the rotation on average. So you can actually calculate based on the speed, rotational speed of your disk. You can calculate the rotational delay, the average rotational delay. It's a few milliseconds, typically. Seek time depends very much on how far you need to seek. So if it's well organized, I mean, you've done organization of your files, right? What is it called? Defragmentation. Very good. I actually forgot it. I wasn't. So it's a good thing that somebody dared to speak up. So, but this is what is happening. It's that things are being moved closer so that when you're seeking, you don't have to go far. Exactly what's happening, trying to reduce the seek time. And so these are the ranges, 1 to 20 milliseconds for seek time, depending on your drive. I think it's getting a slightly better. Rotational delay, again, depends on your rotation speed, but it's order of milliseconds. And then transfer rate, they say about 1 millisecond per 4K by page. This is now, this are becoming very compact. So rotation delay, the transfer time is almost coming 0. What you really need to worry about is the seek time and the rotational delay. So have you heard the difference between sequential and random IOs? Sequential IOs are when you're looking at sectors that are on the same track, basically. Whereas random IOs, they're scattered all over the place. When you have sequential IOs, you only pay 1 seek time. Just move the disk heads there, and then you're just waiting for the thing to come under. And actually, in that case, transfer time might be something. It's part of the rotation. Random IOs, you're paying seek times all the time. You're always moving the head back and forth, and so it's a lot more expensive. So we like sequential IOs. We think they're great. Very important. Solid state disks, they're actually, reading on solid state disks is always fast. Writing, there could be a difference between sequential and random IOs, depending on your disk, or they could not be. If you have a good disk, they'll mask the whole thing. If you have a bad disk, you'll find significant differences. But remember this model. We like, we try to arrange pages on disk so that we get sequential IOs. And this is what the database system does frequently. And again, this is what the defragmentation does. It's just arranging things so that they're together. That's all it does. And so those are the concepts. So remember sequential versus random when we talk about types of indexes, clustered versus unclustered. We'll get into this big time. It's really important to know, and it's really the key to performance. Do modern database systems behave different solid state versus? I would say no, but tomorrow's systems will. So far, I don't know of any system that really is doing a good job of this. What's happening though is that many of the disks are doing a very good job of masking the behavior. So it's more development of the disk that's improving than of the database systems. But this will happen for sure. And basically, when you can start assuming that things are on solid state disk, then you can. Now, I'm working with a company here that's doing video indexing, and they're rewriting the software for solid state disk, and it turns out to make a huge performance improvement. The fact that you can do many small reads and it doesn't matter. So there should be impact. It will get there, but it's not there yet. Good question. Any other questions before we stop? All right. So we start looking at more about into the file organization and going to queries, and you're going to start reading immediately, because otherwise you'll be in trouble. So thank you. Okay, stop.